So, are there any questions before we get started on anything? Are there any problems? Everyone's kind of get on. Everybody's good. All right. So what I want to do is I want to pick back up on continuity. We're going to talk about this last topic on continuity. So, we were talking about continuity. We love continuity because with continuity, we evaluate units by substitution. So we saw all of these rules, right? We said in-algebraic combination, continuous functions, discontinuous, decomposition. The composition is the hard part. If I have time, I will make a little practice quiz for you so you can practice recognizing the form. The hardest part of calculus is when you get to integration, use substitution, and you do derivatives to change it. And if you understand form, you start to get into this habit of saying, oh, I know what that is. That's a composition. That's a product. When you start to get into that mindset, it will make the rest of this class. We'll see. I hope I have time. Okay, so the last thing I want to talk about with continuity is the intermediate value theorem. So continuity is cool for three reasons. First, we can use it to evaluate limits. We're going to see later on down the road, we haven't talked about this yet, but continuity is a necessary condition for a derivative to exist. So if the function's not even continuous, the derivative can't exist. That's a nice thing. But this is the third part of continuity. There are a lot of theorems in mathematics that deal with continuity. Continuity buys us a lot mathematically. And here's kind of an example of this. And by the way, I mentioned I'm making a screencast of this, okay? So I know my handwriting's not the best. I tried, but you can always go back and watch it. These are the people technically that are out for the hurricane, but I'll generally try to make a screencast. So here's what the intermediate value theorem says. There are a few phrases that are really important. It says that if f is continuous on a closed interval, and this is so important, I'm going to rewrite it a little bit differently. I'm going to say f is continuous. I'm going to just use CONT, if you don't mind, on a finite closed interval. There are closed intervals that aren't finite, so technically it will go. Just some lines saying if I have this condition satisfied, like this function here is continuous, right, on a closed interval, the right-hand limit exists, that's equal to the value of the function, the left-hand limit exists, it's equal to the function, and the function continues. If I have that condition, and I have any value between the value of the function at the input. Here it just happens that way with less and f of b. So it can be and if I pick a value intermediate, this is where the intermediate part comes from. I'm going to pick some value, we'll call it capital M, okay, between these two values. What the intermediate value theorem tells me is that there is some value of x. There exists at least one value of x, so that f of x is equal to this intermediate value. And you might say, well, what's so great about that? That seems kind of obvious. Well, first of all, it is kind of obvious. The proof is a little tricky. But if you think about it, doesn't it make sense? You know, if you're continuous and you're traveling along this road, right, and you have to get to here, you better be able to pass through every single value. You can't, you're going to have to jump somewhere. And that's going to contradict the fact that the space will continue. That can't happen. So it kind of makes sense intuitively. But why do we care about this function? Well, I'm going to say two things about it. The first thing is that this is an example of what's called an existence theorem. In other words, it says at least one exists. No one exists. I mean, this is a perfectly fine continuous function too, right? And I chose this value between the value of the function and notice it goes more than that. And that's relevant. That's not a trivial point. And here's why it's relevant. There are a lot of uses to the intermediate value theorem, but one of the best uses of it, one of the most common uses, is when you have a function and you want to find the zeros of the function. In other words, you want to find the values of x to make this function zero. That's the same as asking for the root of this thing. This is my function. I want to know what's equal to zero. This is the same as the root of linear quadratic equation. And you have it. You can the zero equation define the root of solution to a cubic equation. Is there a formula for the cubic equation like the formula? Yes, there is. Is there one for the chordal equation? It was by x to the fourth polynomial, or x to the fourth polynomial. Is there a formula for that?
Yes.
There is. And what about the quintet? Is there a formula for that?
Yes.
No. You would think, and I mean, this is a really amazing fact. Everyone would assume there was. And then back in the early 1800s, a guy called Galileo, he proved that there was no general formula for the thing. It just blows you away, or you would not expect. And it's also true for all higher order formulas. There is no formula. By the way, even there is actually a formula for this. Has anyone ever used the cubic equation? The root of the cubic equation? Was it easy?
That was many years ago. I have no idea.
I can tell you my first book was probably you can do my but it's extremely difficult. And the chordal equation is difficult. The chordal equation, you have to solve the solution of the cubic equation, which is a pain in itself, and you put that solution to get more complex. So even though we don't need intermediate values there, it's going to really come. Let's see how we use it. So here's the idea. I want to find the roots of a function. And what I'm going to do is I'm going to find an interval so that at one endpoint of the interval the function is negative and the other interval is positive. And that's going to guarantee that it's very clear that negative and positive value. There has to be some value of that for the function. Let's look at a concrete example. So here's this function. I want to look at the roots on. I want to see if there is a root between x equal to 1 and x equal to 2. So what I'm going to do, I have a closed interval, right? I'm looking on this interval here. So I have a finite closed interval. So that condition's checked off. Is this function continuous on that finite closed interval? Sure. It's a polynomial. So my function f of x is going to be continuous. 4x2 minus 6x squared plus 3x minus 2. This is continuous on the closed interval 1, 2. So now what I'm going to do is I'm going to look at the function at this endpoint. So the function at the left-hand endpoint is equal to 4 minus 6 plus 3 minus 2, which is minus 2 plus 1, which is minus 1. So this is the value of the function backwards. All right, what is f of 2? Is it important or just like what I know? What was that? Okay. Yeah, I know. It's okay, so let's look at f of 2, right? So it's 4 times 2 cubed, which is 8, minus 6 times 4 squared, which is 4, plus 3 times 2 minus 2. Just simplify that down, right? 32 minus 24, plus 6 times 2, so 8 plus 4 is 2. So notice that I have a function continuous on a closed interval. It's negative at 1 point positive at 1. So 0 is an intermediate value. 0 is between minus 1 and positive 12, right? So what the theorem tells me is that since 0 is between minus 1 and 12, there's some value of x by the intermediate value theorem, 0's between this, so there exists of x is equal to 0. And moreover, there exists an x in that interval. Okay. I'm putting in 1 and 2 because I want to show that this is negative here and this is positive here, and the function has to factor 0. That's what I mean. As long as there's a sign difference on both sides, I know that it's going to have to factor 0. Now, how many times could it have 3 zeros? Could it have 5 zeros? It should have 3%. So it's pretty much quadratic. Quadratic can have 2 roots, right? 2 roots can have 3 roots. I don't know. So how do I find it? So I'm just going to tell you this kind of true. There's a lot of different ways. You kind of learn these things. But here's one way, which is kind of neat. It's called the bisection method. This is just for fun. Bisection method says, okay, I know I'm between -1 and 2. Let's cut the interval in half. Okay. And I'm going to look at the interval -1 to 3/2. And what I really care about is what is the sign at the 3/2. Okay. So what I want to know is what is the sign of f of 3/2. So you put this in your calculator, computer, whatever computers do all this. You'll find out it's positive. Okay, when you go through all the computations, you'll find out this is positive something. And you can verify that. But okay, so that's kind of cool. Any questions about intermediate value? Well, very often you have to solve for like you have this question so let's see. You have a and you want to stop and figure it out. And you want to right at the velocity. Whenever you're interested in a function equal to a certain value, that's equivalent to talking about what is this. You get equal to 5, what does that happen? That happens where root of 2 minus 5 is equal to 0. And you'll see, don't worry, we'll come back to the game and really. They're also important to be critical values. Okay, it's called optimization. Good question, good question. Always have to ask yourself, why do we care? If you have that question, all right, other pieces. So, last thing I want to talk about And the good news is it's all downhill. 2.6 and 2.7 are either easy or they're kind of a rehash of stuff that we've done, bringing things together. So what we want to talk about in section 2.6 is the concept of a limit ad infinitum. And here we have to pay attention to words. So we know what an infinite limit is. And it's kind of interesting to note that an infinite limit is really a y-axis, right? So what it means to have an infinite limit as x approaches the point, the value f of x gets larger and larger and larger and larger and unbounded. So infinite limits are equivalent to vertical axis. And people are asking about asymptotes. So that's kind of the relationship. But we're going to switch gears now. We're going to talk about a thing called limit ad infinitum, not an infinite limit. And so this is asking what is the behavior of the function doing as x gets bigger and bigger and bigger. And it's not so obvious like that, right? As x goes from big, the function increases that down, decreases that down, it's still right, right? So sometimes you can settle down. And that's the kind of limit ad infinitum. The limit at infinity, what it's saying is, as x goes to infinity, the value of the function is kind of settling down to some value. And that's the particular thing. So, limits at infinity, when they exist, is all conditioned on the function existence. When it exists, it's a horizontal line. And the value of y is a horizontal line. So here it's x is increasing the top line. F is increasing. With infinite limits, x is approaching the finite value. F is becoming the value. Now, because we're experts at limits, I want to kind of point out what this means, okay? Because the interpretation of limits is not how the so what I want to take all the time to learn about it is that when I say a limit exists, and when I say limit exists, I'm talking about contact with limit. When a limit exists, it's a claim that the function is placed in the box. And you can just make a limit place. The function is placed in the box. This is the claim. And the way people think about limits is like a challenge. Okay, you're claiming your place is value. Therefore, you have to be able to close by one feature. And so we draw this little game. It's, again, it's a little over the cartoon. Step over this line. Step over this line, right? You keep putting a little dance. I'm very good at this one. I feel like very good at this one. You keep it coming where it is. You say, okay, you're claiming to a question now. I want to see if you can get this close to that. What I have to do is I have to produce, with the burden on me, I have to produce some value of x. So once you're that far, or further, I think that's staying that's the goal. And if you think about it, these conditions are if you keep making these bands smaller and smaller, what's going to happen? Well, you keep executing the people on top of that. This is what this is saying. Where is it distinctly squiggle? It doesn't mean it has to approach it from one side. You don't have to know that, but I'd like you to think about it. I think understanding what limits means are important. So, we're going to have this problem with limits at infinity. And we thought finite limits were hard, right? But then continuity can do that. Although we have to publicly calculate in the simplicity form, nevertheless, at the end of the day, if our function is continuous, the limits become our function. So there is a finite value of that, and we have a way of doing it. The question is, how do we evaluate the limits of infinity? Well, we can try the same thing with the exist, right? We can make tables, right? We can make plots. Not so obvious. We've got a lot of functions that grow very, very, very slowly. If you look at the functions, not so slow. And we're going to see later on, and again, I'll show you this for fun. The natural, that's okay, I won't. Just take my word for it. That these are not always the best ways to proceed. Plots can be very deceiving. And so it's one of the reasons why we use plots in mathematics to kind of guide our intuition. So we never believe a plot to have a real way of doing it. So, you know, people are having these plots, you know, later on this time, so it looks like that's actually going to be a one, I don't know, a lot of that same function, you know, it seems like it's going to be but what if it's not one? What if it's order of 0.9999999? You might say, who cares? Well, it's makes a difference. If you're sending a person to Mars, that's a good thing. It could end up being important, right? So we would like to get the exact answer. We are going to Mars, right? I think that's the new thing. Personally, I won't be disappointed. Okay, so there's two facts we have to know. First off, the proof that infinity is easy in continuity. The first theorem says that if R is any positive number, it can be 0.5, it can be 0.001. Okay, if R is greater than 0, then the limit as x goes to infinity of 1 over x of R is 0. So the reason why is because what's happening? If R is greater than 0, as x increases, x to the R increases. And it actually increases without bound. Again, it's kind of tricky. If you look at the square root function, the fourth root function, it kind of looks like they're plateauing off, but they're not. They do keep going up. They just grow really, really slowly. So let me write this a little mathematically real quick. As x goes to infinity, x to the R goes to infinity, which means 1 over x to the R goes to 0. This last part of the logic is really important. And the plot is that this is what's going on. If I look at x to the R, you know, it's going down like this, okay? Something like that. I'm going to change this. Let me change this. Let me make this x to the R instead of 1 over x to the R. This is infinity if x is greater than 0. I mean, if R is greater than 0. Any power, not positive power, they may increase really, really slowly. The 10th root of x, you plot that. It increases really, really slowly, but it does increase a lot. This is a fact. And again, you can prove this mathematically if you really, really want to. But we won't. So you notice that the hardest thing in class, without a doubt, is dealing with the limit of ratio. This is the big problem. And here's how we deal with limits of infinity when we have ratio. We look at a thing called the leading power. So what I'm going to do, whenever I see a ratio, okay, I look at my form, what do I have? I have a rational function, ratio, right? I'm taking the limit on infinity. So I'm going to look at the leading term of the numerator and denominator. Okay? So the highest power of x in the denominator, this is called the leading term in the denominator. And this is x squared. In other words, I look at the power of each term, right? I have an x squared and x to the third. The highest power is x squared. That's called the leading term. Why do you put the up to that number. And I have X dollars. You have $1. I have $10. I have $100. I have 10 pounds. Okay? $2. That's so if you have I have $1,000, I have $200. So if you really spend on $1,000, that's what we're talking about. We're going to see why in a second that's important. And we're going to do the same thing for the enumerator. So I'm going to look at the leading term and the numerator. Leading term in the numerator. And that's also x squared. And what I'm going to do is I'm going to drop everyone else. I don't care if you think about the function, right? That x is not determined what happens in that function. So I'm going to only keep the leading terms in the numerator and denominator. And so now I'm going to get this. I just drop everyone else. I just ignore. So I have 3x squared over 5x squared. So that's a constant function. 3 over 5, that's a constant function. This just goes to infinity. You can see that one of three things is going to happen, right? Either how the numerator is going to higher, the numerator is going to happen. Or the denominator rate, power to the denominator. What's going to happen? Not only is there two terms, I'm still going to have an extra power to the denominator. That is going to get big. Or the power. And the power that makes it the whatever the ratio is. So let me just, I'll give you, let me give you three, I'll give you an example. So this is an example where they tie. Suppose, for example, this became x to the fourth on top. That would go to infinity. If there was no x squared term, it would go to 0. No x squared term on top. The questions about, now the book, I'm going to tell you that the book goes through a lot more complicated here. The book says you can divide by the power of the leading term in the denominator. You can do that. So I'll show you what the book does if you like to do it this way. I like to do things easy myself, but the book does it this way. The book says divide every term by the leading power in the denominator. So that was x squared, right? So the book would say, okay, do this. Then you're going to go ahead and you're going to cancel things, right? And so you end up getting this. 3 minus 1 over x minus 2 over x squared, 5 plus 4 over x plus 1 over x squared. And then you can use the fact that if x goes to infinity, that goes to 0, that goes to 0, this goes to 0, and this goes to 0. Of course, there's more than one way to find it. I like to do the questions on that. I told you to do this. here. A little bit complicated for that. You have to watch the So let me just illustrate this. The only thing you have to be a little bit careful of. So for limits at positive infinity, what you said is absolutely correct. For limits at negative infinity, let me just show you this real quick, just to make sure we're all on the same page. So suppose I gave you this, and in fact this is a good problem to think about. Suppose I gave you the limit as x goes to infinity of t to the 3/2 minus 5 over t plus 2. Actually, you know what, let me, I'm going to make x go to, let me do t for this t. T goes to negative infinity, sorry. T goes to negative infinity. I got to be careful with this, right? Because I'm going to have a positive root, so this does not exist. Right, because this doesn't even exist. If I go ahead and I try this, I'm going to end up with the square root of t. That doesn't exist. So we got to be careful when there are roots involved. If this was the limit as t goes to negative infinity of t to the 4/3 minus 5 over t plus 2, okay, my leading term in the top would be, and I'll make this 5t. The leading term on the top would be t to the 4/3. The leading term on the bottom would just be t. And so I get the limit as t goes to minus infinity after I cancel out exponents of the cubed root of t. T to the 4/3 minus 1. This is what I can measure because so negative infinity is a little bit of a trick. So this is an example. What would happen here? I drop all these terms, the leading term is x cubed, the leading term is x squared. Okay, I'm only looking at this ratio right here. I cancel them and go to after a while, you don't have to even really do that. You pile on top, you pile on bottom. Let's see. So what about this? This is an interesting one. This is at the end of section part 2. So whenever I see negative infinity, I get careful. I don't keep hard on it. I look at things careful. Okay? So here's what's going on. Let's go ahead and work it out. Leading term on the top is x squared. I mean on the bottom is x squared. Leading term on the top is x. Yeah, I skipped a few pages. I want to get to the ones that are more challenging. Okay, so leading term on the top, the highest power of that is x. The leading power in the denominator is an x squared. So the limit as x goes to minus infinity of 1 over x. It's negative, but what happens is One trick you can do sometimes with limits, well, no, I'm not going to this is now, listen. That one that I gave you a T, right? So this is one that you really do have to be careful. Okay. So this is one as you're going to negative infinity. This does not exist. Okay. And this goes to negative infinity. So you have to be careful. When it goes to positive infinity, right, because when you have roots and go to negative infinity, all of the roots are negative.
Basically, you can look at the odd root, because of the number on top of the larger than the bottom, going to 0.
The limit, hold on, so it's
Or not example at negative infinity. So you can make it fit just like how the approaching positive infinity, if it's larger on top and the bottom, then
right. One of the things you want to have, like I get all the top and bottom, top and there's an index of positive power. Now you just have to be careful and make sure that positive power is not being it's not a combination either positive you just kind of have to puzzle through. But you're right, you could make up a set of rules. I just usually kind of puzzle through it. Okay, so here is so roots are always the hardest part when we're dealing with limits at infinity. So let me give you a few examples here. I'm going to go to the third part of the notes now, for 2.6. So if I want to look at this example, t goes to positive infinity of this function, how do I do that? I'll get an extra point. I'm sorry, what is it? Okay, so when I look at the numerator and the denominator, what's the leading term in the numerator? What's the power of this term right here?
1.
So t times the square root of t. What's the power of that? I have to express it as power, right? So I have to do something, I have to convert that root to a power, right? So I'm going to use a fact here. I'm going to use the fact that the square root of t can be written as t to the 1/2, right? So now, I'm going to have t minus t times t to the 1/2 over 2 t to the 3/2 plus 3t minus 5. So roots, we're going to have to convert to fractional form. Yeah. Exactly. I did that cold-bloodedly because my next step is I'm going to want to combine these exponents, right? So x times x, what is that? X to the first plus first, x squared. So when we multiply like bases, we add their exponents. Now I know how to do this. So the 1, there's a 1 here, right? 2t to the 3 plus 3t minus 5. So now, what is the leading term on the numerator? Right. So I get rid of him, right? On the bottom, what's my leading term? But the 3 is bigger. Isn't the 3 bigger than the 2? Isn't the 3 squared the leading term? Why not? It's an extra number, not the coefficient. This could be 10 million, I don't care, right? So I just eliminate everybody else. And I can do that so nicely because I have a little eraser here. I get rid of everyone else, just do the leading terms, and now they're tied. And so I go ahead and I cancel the t to the 3 halves, and I'm going to get minus 1 half. Questions?
So can we always do this, or only
You know what Sunday after that?
I mean, correct and numbers and everything is just
Where you have to be approaching infinity. It should only work because what we're doing is we're looking at the leading term. The idea is that I can't ignore all the rest of them as t goes to infinity, right? So x goes to infinity. Let me give you a really hard one, okay? So let's look at a really hard one. And by the way, this is exactly the same. If everything is inside the root, I can drop everything. But let me give you a hard one because you guys are just ready for a hard one. This is an interesting one. Let me work this and I'll come to the hard one. So notice something really interesting. When we had limits at a number and we had ratios, we had this problem sometimes of 0 over 0, right? So like that one minus the square root of x over 1 minus x, as x went to 1, they both went to 0. You can have the same problem as a limit goes to infinity. Notice this goes to infinity and that goes to infinity. And infinity minus infinity doesn't make any sense. We don't have any way mathematically of thinking about that. So what do you think we do? When we have limits of roots and we get stuck like this, what do we always do? There's only one thing we need to do. Exactly. See, our bag of tricks is really limited, which makes things nice. So I'm just going to multiply by the conjugate. I have no idea what's going to happen. So what is the conjugate of this? It'll be the same, but there'll be a plus. I have to multiply top and bottom, right? You want to be really careful. You know, with your brackets and all, okay? Okay, so this is the conjugate. All right, and I can simplify the top, right? Because I'm going to have this squared minus this squared, and of course, when I square a square root, they're inverse functions; they undo each other. So the top becomes limit as x goes to infinity of x squared plus 1 minus x squared over x squared plus 1 plus x. And actually, this is going to illustrate the harder problem I wanted to do. So I'm going to kill 2 birds with 1 stone. Notice what happens now, right? Is that these guys are going to cancel. I'm going to be left with 1 over this. So my x squared on the top cancel, and I get 1 over x squared plus 1 squared plus x. The question is, what does that go to? And I'm gonna put a little finer point on that. That's absolutely right. I'm gonna put a little finer point because sometimes you're gonna have a weird case, which is you're gonna have a numerator denominator that has both a polynomial and a root. Okay? Not a polynomial on the top and a root on the bottom. But in one thing, numerator denominator, there's a power and a root. That's what I have here, right? I have a power and a root. And what I'm going to do is I'm going to only look at the leading term in the root. Okay? Because again, the highest power dominates everything. So what I'm going to do here when I have a situation is I'm going to look inside the root and I'm going to find the leading power in the root. The leading power in this root is x squared. That's the leading term. I'm going to drop everything else inside the root. Else in the root. And let's see what we get. Limit as x goes to infinity. And I have the square root of x squared. I can do that. Which is 1 over 2x. Which now I know unambiguously. Notice that I'm writing this equal. You might say, that's irrelevant. These things aren't equal. No, they aren't. You're absolutely right. These two expressions are not equal, but they're limited. That's what lets me do this. Okay? I'm not claiming that this is equal to this. I'm not saying that. But what I'm saying is that the limits are the same. The limit of x and the limit of x squared are the same. They're both positive infinity, even though they're totally different expressions. So when you have a root, it's the same thing. Only take the leading power in the root, drop everything else, then what are you going to have? You're going to have a fractional power. And I can deal with that. That's the only term. If you can hit that, you can knock them all out of the park. Questions? We have 2 minutes to spare. We're ready to go on. Okay, try that. Again, if you run into any trouble, let me know. I'll be in my office all day today. I'm always available on the weekends to Skype and to meet. To make sure that you get caught getting caught. Name games. Well, I already missed one today. See what you call. Go ahead. And okay. See, the cool thing is, you guys sit in the same places too. So that's going to help me a long way. All right, thanks. Have a good weekend. You can keep it now. I got